Welcome back to our course on industrial organization. Last week we started with horizontal product differentiation and looked into really bourgeois pricing in an oligopoly setup where firms had or offered products which were horizontally differentiated. We did that mainly we started with this model of horizontal product differentiation based on a linear quadratic utility function, which you see once again here. Our example was one with a duopoly, Pepper Richards Norman. Real world example here was Coke and Pepsi. And we saw that this linear quadratic utility function gives rise to a very nice linear demand function. And we can play around and can derive a so-called Bertrand-Nash equilibrium based on this demand and utility structure. What we are going to do today is applying or addressing the same kind of questions, again, price competition in a model of horizontal product differentiation. But now we employ the model we already introduced when we addressed the question whether a monopolist over or under supplies product variety. We do that in the so-called hoteling model of spatial price of spatial competition. So we use that, and you already know we had this main street of 1 kilometer length in which consumers were uniformly distributed. We assume for the minute that we now have two shops. These two shops are now operated by competitors, and to start with, we assume that they are located at 0 and 1, that is at the opposite ends of the street. And yeah, that's what I already told you. The shops are competitors. Each consumer still has unit demand and has a reservation price of V. And of course, again, the consumers buy there where we have the lower full price. What is the full price? The price including transport costs. Here again, we have our transport cost T per unit distance. And this is again the wear and back unit cost. And this gives rise to the utility function we have here, our consumer K, which buys from shop, hopefully, our consumer, here, I just did it just the other way around here. We have a consumer I here, which is located here at Xi and buys at a shop located at Xk at a price Pk. Okay, I just mixed up these super and subscripts here. Okay, so what is clear? Indirect utility, you consume the good, so you get V, you have paid a price. So for the product which the shop K charges, so this you subtract this, and you subtract the transport costs. Of course, we use here this absolute sign because only the length, not the direction of the distance matters. And of course, we multiply this length, say 200 meters, with transport cost per meter. Okay, that's what we have, and that's what we already introduced above when we discussed this monopoly problem and the problem how many shops will a monopolist operate. Here we first of all look into how does competition between these two firms look like, which are located at the edges of this street, and which prices are they going to charge. That's our next question. I already showed you this picture last week already. So we have two shops located at the edges. And again, we charge, I was too quick here, we charge some price here. Suppose firm 1 charges this price P1, firm 2 charges this price P2. And then these lines give us the respective costs. So if you have a consumer who is located here, the price inclusive the transport cost would just give this here, okay? That's clear. And again, now we are looking for the so-called indifferent or pivotal consumer who just gets the same utility from buying at either one of these two shops. And so again, the slope of these curves would be just the transport costs T. Okay, so yeah, that's just what it is. So XM marks the location of the marginal buyer, the one who is indifferent between buying either firm's good. And all consumers, this should be clear, these consumers here have much lower. Oh, this was the, I don't know whether you heard that noise. That was from the animation from Pepper Richards' Norman slide. I was too quick here. This consumer here, of course, has much higher utility from buying at shop 1 rather than at shop 2. And everyone to the left goes to shop 1, everyone to the right goes to shop 2. And if shop 1 increases its price, XM moves to the left and some consumers switch then, of course. That should be clear. Now, what the interesting thing is, of course, how do we determine XM? And that's straightforward because we know this indifferent or marginal buyer is indifferent between buying from the shop located at 0 and from the shop located at 1. That means its utility from shopping, from buying to the left is the same as the utility from buying to the right. We just introduced here the location XM and the location of the shops 0 and 1. And now you see immediately the V drops out here. And what you get is that the left-hand side is equal to the right-hand side. And of course, it's straightforward to solve that for XM. And XM is just the location of the indifferent consumer, but note that XN is something between 0 and 1. It's just the share of consumers who buy at shop 1, okay? And of course, 1 minus XM is the share of consumers who buy at shop 2. And what you immediately see and what should be straightforward is if both firms choose the same price, and they are, of course, here located symmetrically at 0 and 1, each one would get half of the market. So because you would have T over 2T, it's just one half here, okay? That sounds rather sensible. If firm 2, shop 2 increases its price, the market share of firm 1 will increase. If firm 1 increases its price, its market share will decrease. And of course, so this is a fraction of consumers who buy from firm 1. That's what I already told you. If, in a sense, there is a total number n of consumers, and we know that firm 1 gets this share, we know that demand will be just the share times the number of consumers. Okay, that's just n times the XM, and this is just stated in full here. Okay, now, as you always, now we have got the demand function, and once we have the demand function, everything is solved because we can simply now set up the profit function, take derivatives with respect to prices, solve for burst response functions, and solve for the Bertrand-Nash equilibrium. That's what we are going to do right now, okay? That should be clear. And of course here, demand for firm 2 would be just firm 2 share would be just 1 minus XM, okay? And D2 would then be n times this 1 minus XM. Okay, yeah, then the profit is simply here the profit per unit, price 1 minus the marginal cost times output. And if we simply rewrite that and take the first derivative with respect to the price, we get the first order condition here. And from this first order condition, so this is just a very easy and straightforward kind of derivation, we of course set that equal to 0, and we solve that for P1 in order to obtain the so-called best response function. Okay, and I think, I just forgot whether we have that on the others. I think it's on the next slide. Of course, what is clear here is that the best response function for firm 2 will be just analogous. It's symmetric. So instead of price 2 here, we will have price 1 here and just the opposite. Okay, and what we have here, best response functions, we can just draw these best response functions. And already what we did already last week is we drew this best response functions, and the important point is that they are upward sloping. Okay, these are so-called strategic complementarities. And you see if you have some price P1, the optimal reaction of firm 2 would be this price, and even with a myopic Tâtonnement process, you would end up in this equilibrium here. You can immediately solve for this equilibrium. That's what we do on the left-hand side here. And what is clear in equilibrium, as everything is symmetric, we will get P1 is equal to P2. And we have a very nice result here, namely that the price is nothing less than marginal cost plus some absolute markup, which is determined by the transport cost T. And that's what's stated here. What is obvious, clear in a symmetric equilibrium, each firm will have a 50% market share. That's not very, very surprising. But what is interesting here is that the markup is determined by the transport cost, and we have a constant absolute markup. And of course, markup, and of course, we could also just substitute that into the profit function. You see the profit is simply P1 is C plus T. The profit is simply T times demand, and demand will be just 1/2 N. Okay, that's what we have here. So you see it's straightforward to derive the profit. And what is clear, the profit depends really totally on these transport cost T. If transport costs were 0, prices would be equal to marginal cost, and we would be back in our Bertrand paradox world with homogeneous products. Because if there are no transport costs, it doesn't matter for each consumer at which shop it buys, okay, or he or she buys. Okay, and so what you see here, these increasing or transport costs are really decisive. Higher transport costs just mean more loyal customers, more inertia, more inert customers who are just rather unwilling to move to the other guy. So the shop which is located closer can charge a higher markup. So that's the important point here, and that's a nice result which you see here. Okay, what the very interesting thing about the hoteling model is, and because given just this result, this is a very similar result as what we derived in terms of our linear quadratic utility example with Coke and Pepsi, where just we had this factor of substitution, which was called S. And if S was 1, then we had homogeneous products, and we also received price equal marginal cost. Now, the interesting thing about the hoteling model here is that we can endogenize product differentiation. What does this mean? Now, here we assumed for the minute that these firms chose the edges of the market or were located at the edges of the market. That is, in terms of our linear city, they were as far apart as possible. That is, we observed what economists call maximum product differentiation. These products were as different as possible in terms of design or in terms of real location. Okay, they were different. And the question is now, and this is what we can address in this model, will they choose actually these kind of maximum product differentiation, or we will rather choose minimum product differentiation, which would mean that they are located at the same spot, okay? Or do they something in between? So the point is here, in general, firms can influence the degree of product differentiation by choosing these product characteristics. We will later on discuss these product characteristics in a little bit more detail, apart from simple location or location here. So firms typically take actions in order to differentiate their products from those of their rivals. That's what we see. We advertise, they try to get a different product design from what their rival does, okay? At least Apple always tries to be different from their rivals. They produce, I don't know, this not sure how this is called, okay? And the important thing is that these activities to differentiate the product typically reduce competition. And so what we want to do is to formally analyze this kind of relationship. And we formally analyze how product choice in this spatial model will look like, and that means which locations will they choose. Okay? And that's what we are going to do right now. And in order to do that, we assume that we have a two-stage game where firms choose both the location and the price, but as it is more complicated to change the location or the design of a product than is to change the price, we assume that the model has an explicit time structure. That means that firms decide on the location of their shop first, or of the design of their product first, and only after both have located their shop or designed their product, they set their prices in the second stage, given these locations they have chosen upfront. Okay, and given we have such a two-stage game, the solution is always by backward induction. We start in the last stage and proceed recursively. We first determine the optimal, the equilibrium prices given the locations. We substitute that into the profit functions, get the so-called reduced profit function, and determine then the optimum location. You will see that in a minute how that works. However, we run into some trouble here in that model if we do that, which sounds rather clear. The problem here with the spatial model with the linear transport costs, which we just had, is that an equilibrium of this game does not exist. The reason is that if the rival is located sufficiently far away from the endpoint, somewhere at 0.75 or something like that, the other firm has an incentive to undercut. And undercutting wins the whole market if we have linear transport cost. But of course, it cannot be an equilibrium where we have one firm choosing such a high price that it's undercut and makes no sense. Okay, and so the problem is really an important one, because that given the equilibrium prices which would arise given some location, you always have, without taking into account this undercutting into account, the firms will always have an incentive to move closer to the center. You can directly derive these equilibrium prices if firms are located at sufficient distance from each other. We don't do that here because we will later on do that for quadratic transport, because you will see you get exactly the same kind of conditions. So this is just that you can check that it's really the case if you want to check whether it's really a problem here with this undercutting. Okay, I just want to give you the intuition. All this has been spelled out by Dapremont, Gabschewitz, and Thies in a famous paper in Econometrica, only 5 pages on hoteling stability in competition. It was, did I already say it was published in 1979? Okay, so what is the point? Suppose here our shop 2 has moved inward, okay? Then if shop 2 chooses some price P2, shop 1 chooses some price P1, this guy here would be the indifferent consumer. Okay, now suppose this firm 1 reduces its price. Then first it gets only a little bit more in terms of consumers, and it reduces further and it gets even some more consumers. But the problem is now, once it sets a price where it were to undercut the shop here, it gets all the consumers in the backyard here. Okay, that is, here we have a discontinuity in the demand function, and therefore also a discontinuity in profit. And given these typical assumptions we make here, and that's what Dapremont, Gabschewitz, and Thies show, you get the trouble that you run into existence problems. Okay, that's what's happening here. So you get everyone, so undercutting so that the consumer located at the location of the rival firm switches to our firm, needs all consumers in the backyard of the rival firm to switch. That's the problem. And a small change in price leads to a jump in demand and profit. Given the pointers, that's what I tried to show you at one of the last bullets on a previous slide. Given if you're here, you always have an incentive to move closer to the center. Why? Because you gain market share given prices, okay? That's why you want to move closer. But the problem is, at some stage, you run into the problem that the other one wants to undercut you. Then you would jump back, but then you have again an incentive to move closer, and so on. That's why we have non-existence here. Okay, I don't want to use more time on this point here. I rather want to present to you an alternative specification or model which just uses a different specification of transport costs. And you will see then we get a wonderful result. And this different specification is just, we assume that transport costs are convex, and to be specific, they are quadratic. You will see in a minute that this is rather straightforward. And the question, of course, how these transport costs look like in reality is an empirical one. Okay, so we have to make empirical studies in order to show that. So here, what we assume is increase more than proportionally with distance. Okay, that's what we assume. That means a small price reduction always leads to a small increase in demand. Suppose shop 2 is here. Suppose you have here this undercut price. Here, this is just nothing as a parabola. Okay, just x squared. You will see that on the other slide here. And the point is here, now, here, of course, you also have this parabola, but now, of course, here, the point is that for someone who is located here, this guy would be the XM. This guy, of course, would be indifferent between buying from shop 1 and shop 2. Okay, because it has zero transport cost here, but higher and the same inclusive price with transport cost given the lower undercut price here. But the point is, if you move to the right here, these guys here, they have lower inclusive prices, that is prices including transport cost, because given that they have their transport costs only increase very slightly, whereas these guys feature transport costs which increase really drastically. And just to give you an example, do you think transport costs are more likely to be proportional, that is linear, or more than proportional? So a typical example I give here, think of a train ride. So suppose your train is not on time. Then you have 100 or say 61 people you have in a train. And suppose that, as always, if you want to go from Gießen to Frankfurt, the train will be late, and perhaps you are on the other train from Licherstraße, from where our department is coming from Fulda or from the Vogelsberg to the Gießen main station. Okay, the point is, suppose you have 61 passengers on this train, and each of these passengers would have to wait 2 minutes because the train would have to be delayed. The train to Frankfurt would have to be delayed 2 minutes so that you are on the other train, catch it. So if it's delayed, these 61 people have to bear the cost of these 2 minutes, okay? And now we, of course, would need some tea here. And whereas you, given that there is not every hour or always a train, suppose you would have to wait for 2 hours then to get your train. And now the point is, hopefully you got this, do you think the transport cost of 61 of the 61 people times 2 minutes are higher, or the inconvenience costs are higher than of this one guy times 120 minutes? Okay. Now, if we had linear transport cost, this 61, or say that's why I use 61, the 61 times 2 would be more than this 1 time 120. But in my personal experience, of course, these 2 minutes hardly matter for these 61 people, okay, because we are here very close to our optimal location and we hardly have high cost, whereas to wait 120 minutes, it will be very convex, this function, and the cost will be much higher. Okay, so I don't know, hopefully it was somehow clear. If not, we can move on discussing that example later on in WebEx. Okay, so yeah, and of course now what we have here, that's an important and nice thing about these linear transport costs. If firm 1 changes its prices a little bit, its quantity will also change a little bit. Okay, so now we have perfectly continuous demand functions and therefore also a continuous profit function. And what we can do is just to do the same. We derive now the demand function. Given we have the demand function, we can derive the profit function and take derivatives, get the first order conditions, get best response functions, and then derive the Bertrand-Nash equilibrium. Okay, now again, same thing as previously, but we just substituted the absolute sign here with the square. Okay, same thing, everything the same. Again, the direction doesn't matter because it doesn't matter whether you're to the left or to the right of the shop. It's just squared, so only the absolute distance matters, and we just get a square. And apart from that, everything is the same. And again, now we allow for locations which are different from 0 and 1. So, but we assume that shop 1 is the shop to the left-hand side, shop 2 is the shop to the right-hand side. That's just what we have here in terms that x1 is smaller than x2. And now we get to our solution of the second stage price game. Okay, given some locations of firm 1 and firm 2, we can again derive the indifferent customer here, or consumer, and exactly the same way as we did it. The only difference here is these squares here instead of the absolute sign, and we do it the same way, and we get xm is equal to this condition here. Remember up there, it was, we wrote down this condition. Actually, if you assume that x1 is 0 and x2 is 1, you get exactly the same, because here you would get 1/2. This is just t over 2t plus p2 minus p1 over 2t, because that would be 1 minus 0. Exactly the same, okay? So you see there is not much of a difference in terms of the results. But again, however, you get interesting results, because again here, if prices are the same, it depends what your market share is, what the locations are. Suppose if x2 would still be 1, firm 2 would be located at 1, but x1 would be 0, would be 1/2, for instance, located at the center, then we would get here 3/4. Okay, so the market share, if you are located at the center and the other one is located at the edge of the market, you get 3/4 of the market. Okay, that's what you see for given prices. You have a strong tendency to move closer to your customer, because you keep all the consumers in your backyard and gain some consumers from your customer as you, or from your competitor as you move closer towards her. Okay, so that's what we have here. And so directly we get the demand for firm 1 and for firm 2 just by multiplying these shares with the total number of consumers. Okay, should be clear. I think that's about what I wanted to say here. So now it's straightforward to derive the profit. Just again here, profit per unit times demand, and the same expression for firm 2 here. Okay, and what we are doing is we differentiate both profits with respect to own prices, take first derivatives here, set that equal to 0, and solve for the prices. I don't do that in detail. I think we have a problem in this assignment here. That's why you can do it and you get it directly. So these are the prices. Okay, now what are these prices here? Now, again, just let's start with a check of what happens in compared to the case we looked into up there with the locations of 0 and 1 and the linear transport cost. You see, if 2 is 1 and 1 is 0, this would be 1. This would be here 3. So it would be c plus t times 3 over 3. It would be c plus t. Okay, so exactly the same result. here with this quadratic transport cost. And again, all the arguments I showed you above apply here. Okay, the price is equal to marginal cost if transport costs are 0, and if with increasing transport cost price, the markup increases. Now, however, and what is also an interesting thing, now we allow for different locations. Now, suppose both were located at the same space. Suppose both were located at 1/2. Of course, both could also be located at 1/4. But of course, as we love symmetry, it would be 1/2 in a sense. If both are located at the same stage here, this would be 0. So we would get price equal marginal cost. And remember our discussion above where we will find maximum or minimum product differentiation. Minimum product differentiation would mean they are located at the same spot, okay, at the same location. And that would mean, however, because they are no different from the viewpoint of consumers, we are back into Bertrand competition with homogeneous products. The Bertrand paradox applies, and we have price equal marginal cost. Okay, so that already gives you an indication that it doesn't seem like a good idea to locate at the same space as at the same spot as your rival. Okay, that's what we have, and of course that applies also for price too. And what we could say more generally, the prices go down as you move closer towards your rival. That's what you get by taking a derivative here of P1 with respect to X1, or also by P2 with respect to X1, or if you take the derivative with respect to X2, you would see if you increase X2, the prices increase. That means if you move farther away, your price increases. So more spatially differentiated products are sold at higher prices. That gives you already an indication of what the kind of result will be. Now, what we are doing next is we derive the equilibrium or the equilibrium of the second stage, the solution of the second stage price game. Now we substitute that into the profit function and get the so-called reduced profit function, that is profit solely as a function of the locations, now only X1 and X2. Again, what we see immediately, if X2 is equal to X1, profits are 0. If transport costs are 0, profits are 0. So both transport costs and horizontal product differentiation are important. And same for the other. Now, what we are doing here, we take, of course, what we can do is we can just take or derive the first order conditions, take the derivatives of profit 1 with respect to firm's 1 location X1. So we differentiate or reduce profit function with respect to their own location, given the location of the rival. And that's what we get here. That's what we get here. And now you might ask why we have this here. The prime 1, the pi 1 over dx1 is smaller than 0. What does this mean? This means that firm 1 has an incentive to make x1 as small as possible. How small is possible, or what is the smallest number? Actually, if we assume that our firm has to locate on the market somewhere between 0 and 1, of course, the smallest number we can get is 0. Okay, and if we look into this first order condition here, so this is straightforward to be derived from up here by just taking a derivative with respect to x1. And now if you substitute here for x1 0, for x2 something which is larger than 0, take for instance 1, so you would see that this guy here is always positive because 2 is always larger than 0 and something positive minus something which is smaller than 1. Okay, this is also of course positive. So this is positive, and here you have a negative sign, and that's what gives you this guy here. Okay, and no, so we see that it always, the firm 1 has always an incentive, irrespective even of the location of firm 2, to reduce its its location, that is to move to the left, okay, as close to the edge of the market as possible. Analogously, we get for firm 2, here we have a minus, but here we have a -4. -4 is always larger than x1 plus x2. Even if both were located at 1, we would get a minus here. Okay, and so we get a plus here. That's what's written here. So firm 2 always has an incentive to move further to the left. So what we get here is maximum product differentiation. Okay, each firm has an incentive to move to the endpoint, to its endpoint, we could say, of the market. Okay, that's the important point. And that's what's stated here. Maximum product differentiation is an equilibrium. It's even an equilibrium in dominant strategies. Even irrespective of what your rival does, you want to move closer to the edge. Okay, the equilibrium price is of course then the same as what we had in the linear transport cost case here. And what is interesting, of course, if we allow locations outside the market area, so they are located outside the city somewhere in the prairie or whatever it is, they would locate not at minus infinity and infinity, but at -1/4 and 5/4. That's what you can directly calculate by just solving that to be equal to 0 and solving this system of 2 equations in 2 unknowns. And so that's interesting. Firms would even locate outside the market. Why? What is the intuition? Yeah, it reduces price competition. Okay, so what we see here, we have always a direct effect here. That's what I showed you for a given price. For a given price, that's what you saw. For a given price, you saw that for a given price, you increase your market share if you move closer to your rival. The problem is, if you move closer to your rival, the effect will be that prices will go down, you intensify competition. And if you do that, you run into trouble because prices may go down until 0, okay? So the problem is here, this negative indirect of if moving closer towards your rival means that prices decrease so strongly that in total, your profits will go down. So the indirect effect, the price effect is stronger than the direct one. That's why you want to have maximum product differentiation. And you see that rather well. I think Hotelling in its original model assumed that firms will choose minimum product differentiation. He assumed that firms will choose agglomeration, that is, both firms will choose the same location. And how did he come up with this result? I think he didn't, and I just look here for this slide here. It's a slide two slides above here. He looked only for a case where the prices were given, say by regulation or something like that. If the price is given, okay, so what here, this is only the profit of firm 1, but of course firm 2 is analogous. If the prices are given, and suppose they are regulated and both firms have to charge the same price, suppose like pharmacies or something like that, then this would be 0 anyway, this second part here. And now what you see, if you're firm 1, you increase your profit by increasing x1. That means moving closer to your rival. Okay? And it always increases. So you would choose the same location as your rival, or at least say 1 epsilon to the left perhaps, but that's what you would do. Okay? That's what you see, and that's very important. And I think we certainly have a problem set or a problem where we discuss that. So it's important, or a very important point is, do we have price competition or not? If we have price competition, we will see that firms try to differentiate themselves. If they don't do, if there is no price competition, we will see agglomeration, we will see minimum product differentiation. Of course, the socially optimal locations, that's what we derived in a monopoly case, is in the case of 2 shops, 1/4 and 3/4. So what we see from a viewpoint of the social planner is, in a sense, too much of product differentiation. What is perhaps also interesting, and I can relate to my own research here, I published a paper in the International Journal of Industrial Organization in 2005, where I accounted for more than 2 firms, I think up to 5 even. If you have more than 2 firms, you no longer have maximum product differentiation. Even if you have price competition. So if you have 3 firms, for instance, you might expect that they are located at 0, at 1/2 and 1, but it's actually, as I wrote in the notes here, it's 1/8, 1/2, and 7/8 would be the locations. Okay, there in this case, if you have such a guy which is located in the center here, then you don't want to be, if you're the one you has a worse position anyway because you're located at the edge, you don't want to go so far away. Okay, that's what you have here. But anyway, so the important point here about this hoteling setup, where we are able to endogenize product differentiation, we see there is a strong tendency or a strong incentive to differentiate oneself from the rival. Okay. Before I move on discussing entry in that model, or actually in a slightly differentiated model, the so-called circular city model based on Salop's paper from 1979, I want to make a short break here and ask for questions in WebEx. Yeah, now we introduce entry in our spatial model, and therefore we use a derivative or a variant of the hoteling model, which is slightly different. We don't use now the linear city, but a so-called circular city, because there it's easier to allow for entry. You will see that in a minute. The question here we want to address is the one: what happens if we allow for entry in our spatial model? Will we have over entry, as we had in our case with our monopolist? You remember in terms of our varieties of the Head and Shoulders shampoo, we found in our hoteling model that the monopolist will over-provide variety. And the question is here, will we have too many entrants? Will we have over entry or under entry? Okay, and so is the amount of entry and therefore the variety of products available or of shops available, will that be too high or too low? An interesting policy question, or how that relates to policy, is in a sense whether we should have regulation of, say, shopping centers and cinemas. When I was teaching this course in Vienna, I think there were 10 new cineplexes built all over Vienna. 2 or 3 of them went bankrupt right away. And the question is, will the market lead to an efficient amount of entry here? Okay, or will there be over entry or insufficient entry? And as I already told you, we will employ the circular city instead of the linear street here. And because why? Everyone is symmetric on a circle. Everyone has a left and a right neighbor. Whereas on the linear street, you remember these 1/8, 1/2, and 7/8 example. The guy located in the center is different from the shops located at the endpoints, okay? Because they don't have a left and right neighbor. If you have a circular city, everyone has a neighbor. And the circumference is again 1 so that is the same as the length with a linear city. Again, once we want to model entry, we have to have some entry costs. We assume that each firm faces some fixed entry cost F. Again, linear transport costs. Now in a second you will see that doesn't matter. And we assume constant marginal cost. And that's what you see here. So you have a circle, you have 8 firms, so these spokes here, or however you would call it, or just notate or denote the locations. Firm 1 located here chooses price P1, firm 8 chooses size P8, and firm 2 chooses price P2. These guys here are the indifferent consumers or marginal consumers from the viewpoint of firm 2. Okay, so this distance would be xm here, and this distance would be xm. So you always have, each firm has a left and right neighbor. We, of course, will apply symmetry. So if we look into the behavior of firm 2, we will assume that firm 3 and firm 1 choose the same prices. So P1 is the same as P3. And so we can then, depending on P2, determine the marginal consumer. Okay. And what is also important here, we assume that all these firms are located symmetrically or equidistantly. Okay. The distance between all of them is the same, and given that we have 8th firm, it would be 1/8. Okay. And if everyone had the same prices, this xm would be just 1/2. And if we have n firms, of course, the distance between the two firms would be 1/n. And finally, remember, we assume linear transport costs. That doesn't matter here, because here you don't, or firm 1 doesn't have an incentive to move closer to firm 2 in order to gain market share here for given prices, because if it gains market share here, it loses market share here. Okay, so no incentive to move away from a symmetric location in terms of this market share gain. Hopefully clear so far. Then we move on. So again, a two-stage game. The first stage is now a different one. Now we choose not the exact location, but now we decide on whether we want to enter or not. That means, do we want to invest in this fixed investment and spend fixed cost F, or don't we? And now if we suppose and enter, what I already told you, there will be an exogenous choice of location. We will have just equal spacing, and the distance between two adjacent firms is 1/n. Okay, so that's what we assume here. That's what is called costless relocation of firms. The firms decide on locations only after the number of firms is determined. That's the assumption. And then they, of course, would again choose maximum distance, and that would give equal spacing. Okay. Later on, we will assume that we don't have this kind of costless relocation, but that's the standard, and that's the kind of model and setup in which it's most easy to treat or to deal with this kind of entry. Yeah, in a second stage, again, we have per truck price competition. Firm choose prices, and demand for firm 2 given firm 1 and firm 3 charge the same price P is just, or we can just derive that by looking for the indifferent customer or consumer located at xm. And what is clear, so these are the transport costs, or the price inclusive the transport cost if I buy at firm 2, and here this is if I buy at firm 1. If I buy at firm 1, my distance, if I'm located at xm from P2, my distance is 1/n minus this xm. So that's my distance to 1, and it's also my distance to 3. So this is symmetric here. I only need to look at one of the two, and of course I will substitute now the P1 and the P3 by the P up here. Okay, and if I have this, it's straightforward to derive these xm, and therefore the share of firm 2. Actually, it gets 2 of these shares, but again, you see it's pretty much the same as what we previously had. And if the price is the same, it's now the share is just 1/2n. And as I get these xm on the left, on the right, the share will be simply be, or demand will simply be, if prices are the same, will be 1/small n, of course, then times the total number of consumers, capital N. So straightforward and almost or really identical to what we did above. And now we are looking into the firm's decision given a certain number of firms, and given each firm charges a price, or all other or rivals charge a price P. And actually, it's not all other. The important thing is that your two neighbors charge this price here. So if we want to analyze the profit of firm I here. Firm I chooses PI, and its profit depends on the price of the other firms, which we assume is symmetric, and on the number of firms. Again, this is the profit per unit times here demand. Taking a derivative with respect to P, we get something. We can calculate, of course, as always, the best response function here, the reaction function, and which looks almost identical to what we had up there. And now, knowing that we are looking for a symmetric equilibrium, we are setting Pi equal to P, and get that the price is very similar to what we had above. We again get that the price is equal to the marginal cost plus some absolute markup, and this absolute markup now depends on the transport cost and on the number of firms active in the market. And the more firms are active in the market, the lower our prices, or actually prices converge to marginal cost as n approaches infinity. Okay, that's what also is a nice result, and it's also what we hopefully would expect, and we are happy that we got this here. And of course, then we get the reduced profit function. The reduced profit function depending on the number of firms. We just substitute this price up here into our profit function. We see our per unit profit would be just T over small n, multiplied here by this expression, and simplified, we get that is equal to capital N times T over n small n squared minus the fixed cost. Of course, fixed costs are decisive. Number of consumers is decisive. Again, the degree of transport cost is decisive, and the number of rivals is interesting. And what is interesting here, if you look into this n, this small n here, the number of firms enters that with a square here, and that means if the number of firms double, you only get a quarter of the profit you previously had. So the profits are decreasing in the number of rivals at an increasing rate. Okay, double of competitors doesn't mean you get half of the profit, but you only get a quarter of the profit. That's rather important, because if you get more firms, more rivals, you get closer to the other, and therefore competition intensifies. That's an important effect here. Okay, that's what we have. Yeah, now what we can look into is to address the question whether the entry in the market system is optimal in the social sense. That is, do we get over entry or insufficient entry? Therefore, we just look into what will be our market number of entrants. That is the free entry number of firms. Here we just set these profit per firm equal to 0. We ignore the integer constraint, so it might be that 22.48 firms enter here. We just ignore this integer constraint for simplicity. We know always if 24.53 solve this problem here, we know that 24 firms could enter. Okay, so each of them would make a small profit, but the 25th firm could not enter. And now what we get here, we just set that equal to 0 and solve for small n. And what we get here is this expression. This expression is rather straightforward. Namely, we get fewer firms in a market equilibrium, in the free entry market equilibrium, if fixed costs are higher. We get more firms if there are more consumers, if capital N is larger. We get more firms if consumers are more loyal, in a sense, if transport costs are higher. What is interesting, however, suppose the number of consumer doubles, you might expect that we also get then twice the number of firms. But however, that's not true. That has got something to do what I told you previously. That's what you see here in terms of the operating profit. If you get more firms, competition intensifies. Okay, that's why you don't get twice as many firms if the number of consumers doubles. Even though you can sell twice as many units, your price or your profit per unit will be lower because competition intensifies. Okay, that's what's an important aspect of this model, and a nice aspect, by the way, because that's exactly what you would expect. Yeah, now the socially optimal number of firms, that's as we have unit demand, it's no question of, in a sense, allocative inefficiency that someone buys fewer units than expected, but it's just a question of minimizing total costs, where total costs are transport costs plus production costs plus fixed costs. That's exactly what we had here. This is just a copy of a previous slide where you see we just need to calculate these triangles here. This area was equal to t over 4 times 9 squared, and what we got there was exactly these kind of cost, and that's why you get this expression here. And now, once you want to minimize this, you just take the derivative with respect to n. Again, we ignore the integer constraint, and we get this solution. And what you directly see, if I wouldn't have drawn so many lines here, what you directly see, this is just 1/2 of our market solution. Okay? And what does this mean? We get overinvestment or over-entry in this free entry equilibrium. So the market oversupplies variety here in a sense. And we get an excess supply of variance. Why is this so? This is due to the so-called business stealing effect. What does this mean? Actually, what is decisive when you decide about entry? Decisive is whether you break even or not. Okay, how do you break even? Actually, or what are the effects of your entry? There are actually two effects. First of all, of course, consumers now have to travel less, and therefore their transport costs decrease, but to a large degree, your profit comes from the profit of rivals. You just shift profit from rivals to you. Okay, and that's what is called business stealing. And this business stealing, this is just a redistribution of profit from one firm to another firm. Of course, from a viewpoint of a social planner, this does not increase social welfare. This is just a redistribution and leads here to overentry. Okay, you get actually a similar effect in the Cournot model. This is a famous Mankiw-Winston model where you also have overentry in the market compared to a second best in which the government regulates entry, but the firms are free to choose then their quantities. Okay, that's an important point here. Of course, this is only in terms of total surplus, where you don't maximize total surplus. For consumers, it's always better to have more firms in terms of consumer surplus. But of course, in terms of society, it's really important. You waste a lot of in a sense, fixed costs. And if you look at all these many cineplexes or shopping centers, which at some point in time might go bankrupt and might even be abandoned, perhaps it's not too bad an idea to regulate that. At least if you happen to work as a consultant for the city government of Gießen or of some other city, at least you might come up with this model showing you that there is overentry. I think that's about what I wanted to tell you. Yeah, actually, later on at the end of this chapter, I will briefly show you that there are instances or there are models in which we get underentry. These are so-called love of variety models. But here in this model, which is a so-called ideal variety model, where each firm or each consumer buys only at a certain shop and not at all shops, we get these over-entry result. Of course, as always, if you play around with certain assumptions of this sell-up model here, with the transport cost function, with the distribution of consumers, with no price competition, you might get different results, but I leave that as an exercise here. Okay, so, and jump forward to a few other very interesting kind of questions we can address here based on these hoteling or sell-up models of product differentiation. The first one is a famous paper by Richard Schmalensee, to which I want to draw your attention, which takes up the question of entry deterrence. But now, however, not in a monopoly setup as we did in the Stackelberg-Dixit-Spence model, but now in a more like an oligopoly setup. And the standard kind of oligopoly setup is the breakfast cereal industry in the US, because there are, in a sense, dominant firms like Kellogg's, like Oatmeals, and I don't know what else. And the question was there whether these firms, these producers of breakfast cereal, can prevent entry by smaller rivals by what is called brand proliferation. What does this mean? There is an existing firm, and these firms are located on this circle, and each of the existing firms, suppose to begin with, there are only 4 firms, okay? For oats, meals, Quaker Oats, and whatever it is, okay? There are only 4, and now here you see there's really a large space to enter. And then the question was, to begin with, Kellogg's only produced the cornflakes. What they are doing then now, they produce further variants, they bring further variants to the market and crowd the product space in a sense, and then makes it difficult for a new entrant to enter, because then what is left here in terms of market share is very small. Okay, and that's what he really did. Actually, there are a few specific assumptions. For instance, there is no price competition once they enter, and therefore, yeah. So that's critical assumptions. But anyway, the idea is rather interesting, and what they show is, or what Schmalensee shows, is that these firms, these cereal producers, really have an incentive to crowd the product space by bringing up new varieties, and therefore trying to keep rivals out of the market. Hopefully this was somehow clear. Actually, if you want to know more about that, or about a specific application of this idea, look into a paper my colleagues from our chair, Samuel De Haas, Jan Schäfer, and Daniel Herold wrote. They actually analyzed the behavior of Flixbus in the coach market, so in the long distance bus market, where Flixbus is now next to a monopolist, and they analyzed what happened when Flixbus took over Postbus. And what they saw before they took over, before the merger was consummated, they provided much more connections. So in a sense, they were crowding product space. Only after they provided many connections between different cities, so that it was difficult for other companies to also offer a connection in that city-to-city pair. Okay, that was the problem, because it was clear they will only have a low demand for that, given that Flixbus already has 3 or 4 connections between these cities. And what they saw is, once they had acquired Postbus, they didn't increase the price. That was interesting, because the main question Samuel and Daniel and Jan asked was, what happened to the price after the merger? They actually didn't increase the price, but what they did is they reduced the number of connections. Okay, because in a sense they were they were now close to a monopolist and were not afraid or didn't have to fear further entry. Okay, that was interesting because what you saw is they obviously did something like brand proliferation once they faced a lot of competition, but then once the competitive pressure has gone away, they were able to reduce the number of connections. Okay, that's what I wanted to say you here, or to tell you here. Another interesting thing is going back to some slides by Robert Pindick from the MIT. He gives you an example that these kind of product characteristics, this kind of location, need not always be just a single dimension, but it can have several dimensions. So the product space can be more complicated than these single lines, at least 2 dimensions. What you see here, he has 2 different characteristics, namely healthfulness and sweetness. And what you also see here, he just drew the different kind of breakfast cereals which are on offer now here, which every one of you might know is Kellogg's Cornflakes. I typically don't know. Oh, I've heard of Special K, but I don't, and of Fruit Loops, but I don't know most of the others. The point is here, what you see is that the product space is in a sense rather crowded, and you might think that this is part of the strategy of these companies to make it easy, or excuse me, to make it hard for potential entrants to find some spot which is not yet occupied by some product they offer. Okay, whereas I just have a problem with here. How can we have a cereal which is both very healthy and very sweet? So in a sense, I would think that nothing beyond this line is possible. It cannot be very sweet and very healthy at the same time. My problem was always that my kids were only going here in this direction. They only wanted to have very, very sweet but not healthy at all things. Yeah, and you can even do that or do more of that and introduce another kind of characteristic, which would be crunchiness here. So you do that here in 2 dimensions, or you might do that even in 3 dimensions, and it gets more complicated. And you see here, Pindick really did a good job in coming up with even more examples like Captain Crunch or Grape Nuts or whatever it is. So what is interesting, perhaps, if you ever go to a large supermarket which has many muesli, you could do the same exercise with Seitenbacher muesli, which has a Bergsteiger muesli, which has dozens of different types, and they also are somewhere related in this sweetness versus healthiness or healthfulness space. Okay, and the question would of course then be, does Seitenbacher also engage in product proliferation? Perhaps an interesting topic. Yeah, the main question, however, here is, does that really work, this strategy? Does this strategy really work? Is it possible to deter entry by product proliferation? And I think that's the final slide here, based on this kind of spatial models. And there's a very interesting paper by Ken Chutt in the Rand Journal of Economics, published in 1985. It's called Credible Spatial Preemption. So the question is, can the incumbent deter entry by setting up additional shops? Just to let me clear what I mean here. Here's the incumbent shop, and suppose here one incumbent shop, and there's a possibility for the entrant to enter here at 1. And can the incumbent prevent this by setting up a shop here at stage 1, a second shop? Okay, and you will see this crucially depends on the so-called exit cost. And if exit costs are not high enough, you'll see immediately from this figure that such a strategy cannot work. And you will, or does not work actually. You will see that here, suppose shop 1 has some price. What happens here at location 1? You have 2 shops here, That is, they are minimally differentiated. If you have two shops here, one shop by the incumbent and one shop by the entrant, each shop, of course, will choose price equal marginal cost because there is no product differentiation. Therefore, if the incumbent has a shop here set up, the price at location 2 or at location 1 will be C. And therefore, the price will be lower as if there is only a shop by the entrant operated here. Okay, because then the price will be higher. And you see immediately that it doesn't make sense for the incumbent to set up a second shop if the other firm enters, and what the entrant can expect is that the incumbent would exit here. Okay, that the incumbent would exit here. So it's not credible that that the incumbent sets up a second shop, or actually here that if it really sets up a second shop, it will not leave that shop in the market. It will exit this shop unless, and that's what we have here, unless there are very high exit costs. If there are high exit costs and a little bit of fixed cost, of course, then the entrant knows that the incumbent will not enter if there are high exit costs, and the entrant will not enter in the first place. But only if there are significant exit costs. And now you might imagine what the significant exit costs of a further variety of a muesli is. So I guess they are next to ignorable. And this is different, for instance, with a gasoline station, because you will have very high cleanup costs if you want to close a gasoline station. Yeah, that's what we have here. And I think there is a very nice paper or very nice case study by Esti and Pankaj Gemawat, who compared or who looked into the competition between the Airbus and Boeing in super jumbos. So what is here? This product 0 would be the Boeing 747, the jumbo jet, and here this is actually the A380. Okay, and what Gemawat and Esti write is that Boeing attempted to preempt Airbus by what? By introducing some new product, which was not really the super jumbo, but some stretch kind of jumbo. And what they saw, or what they claim, is that it wouldn't have been credible based on these arguments by Chad, that they produce really the same kind of jumbo, so like 600 or 800 kind of passenger capacity. So they could also produce some intermediate product like say 600, but actually that also turned out that it doesn't work, because you would have seen a lot of self-cannibalization. This guy would have been, this Boeing stretch jumbo would have been a competitor to the Boeing 747, and this would have cannibalized and their own product, and therefore have led to a lower profit. That's why Boeing didn't do that. And probably, first of all, Airbus was aided here by some commitment of European governments that they support this A380. And given the recent development, Boeing has to be happy that it didn't manage to develop this kind of jumbo jet, because no one anymore buys these kind of large aircrafts, and I think no one or hardly anyone uses the A380, even without the Corona crisis. Okay, in the notes you will find a lot of more information on this case study, really an interesting one. But again, I presented this just in order to show you an example of the relevance of this kind of arguments. Before I move on with this last slide on horizontal product differentiation, I just want to make a short break here and ask for further questions. I want to close this part on product differentiation with some general concepts, actually just to put that into perspective. What we did in terms of the hoteling and the Salop model was a so-called ideal variety approach. I already briefly mentioned that ideal variety means that given you live somewhere in the city, you want to have this shop right next to you because then you don't have high transport costs and you just buy only one unit. There is an alternative, the so-called love of variety approach. That is, you buy many variants, in former times you bought many different music CDs, and of course, the larger is the variety, the better for you. And the question is, as always, and that's what we just addressed, is how many variants will be provided in a market system? Will there be too much or too little differentiation? We saw that in this ideal variety approach, in the spatial models, we got over provision of variety, whereas in these love of variety approaches, at least partially, you get the opposite result because, due to this love of variety approach, typically where would you assume that you have some identical consumers or a representative consumer, you have some strictly concave utility functions. I will give you an example on the next slide here. And each consumer typically buys all available varieties. And in contrast to the unit elastic demand, unit demand we have here in a hoteling model, each consumer has elastic demand, and you often get this, as I told you, insufficient provision of variety. The standard approaches here are the one I already presented to you. That was the linear quadratic utility function I already showed to you, giving rise to a very nice linear demand function. The next example is the CES or Dixit-Stiglitz utility function, which you first of all might know from the economics of innovation course, but this is a function which is heavily employed both in macroeconomics and in international trade theory. Okay, and the nice thing about that function is you see you have also end products, but it gives rise not to linear demand but to isoelastic demand functions. And I don't want to go deeper into the Stone-Geary. This is a extension of the Cobb-Douglas function in a way. And what you typically have here, you have some sub-utility function, which would be this one here, and you have some outside good, which might be homogeneous, and you get this upper utility function is either quasi-linear or Cobb-Douglas. And the interesting point here, or the difference to the ideal variety approaches, with the ideal variety approaches, you have neighboring products. Here you don't have any neighboring products, even though you might be able to introduce some asymmetry among the products. Okay, but I don't want to go through the details. I already presented in particular this kind of approach up there, and the point is it's always straightforward. You have these utility functions. From the utility functions you derive the demand functions. They might look a bit more complicated here. Typically we do that only in the two product case, or in oligopoly case or duopoly case, and as you saw in the Coke Pepsi example, then it's straightforward to derive the best response functions and the Bertrand-Nash equilibrium. But that's about it. What I wanted to tell you. I have a few more minutes left. That's why I want to do vertical product differentiation as well. What is vertical product differentiation? That is quality differentiation. We already discussed this point. That's why I want to be brief here. We discussed that point already, or that topic, when we discussed the decision of a monopolist whether to provide different or various qualities of a product, okay, a high quality and a low quality, okay? And that's what we want to do right now. We want to introduce competition between two firms in a duopoly, but now these firms can choose whether they produce a high or a low quality. And the question will again be, will they choose the same qualities? Will they choose different qualities, and so on? Okay, that's what we are going to do now. And what we do here is we use exactly the same approach as above. I just could jump back. This was what we did here on slide 200. and 11. Okay, exactly the same approach. I don't know whether you remember it, perhaps not, but you can just look it up. Okay, and what you see is we now assume we'd have two firms offering two qualities, high quality, quality 1, with a quality index C1, and a low quality 2 with a quality index C2. Now the only difference is up there we showed that only the monopolist will only provide both qualities if the quality adjusted cost of the low quality or lower. Now we assume that the two products cause the same production costs, and so that the quality difference is mainly due to differences in product development or fixed costs. Okay, that's what we assume here. Of course, we can do it otherwise, but the interesting results happen if you assume this here. And again, same kind of indirect utility function we had up there. So of our consumer I who buys quality CK at a price PK. So here this I index is just in a sense the willingness for quality, and this is uniformly distributed between 0 and theta, where this might be something like your income. Okay, high income means high willingness to pay for quality. So, and the maximum willingness to pay for quality of a consumer would be theta times Z here. Okay, that's what we already had. We assume that there's a certain number of consumers so that we get some density n over theta here. That's exactly the same as what we did up there. And we also calculated the indifferent consumer or the consumer who is indifferent between buying product 1 or product 2 if they are sold at prices P1 and P2. So this is this guy here. And this is exactly the same kind of condition. I don't know, is it on the next slide, where I show you that. So what you get is here the indifferent consumer, everyone between theta and I then buys this from this guy, and the demand for the high quality will be Q1, or that's exactly what I told you, times n or n times theta minus I divided by theta. Remember, this n over theta was nothing else than our density here. And a similar, we know how many consumers buy. I think that's what I can show you here. Hopefully this, even though this is a different example, but this is exactly what we had up there. Okay, so here is our indifferent consumer we had up there. We just derived, and here is this guy who has just a willingness to pay of 0. These guys buy at this prices here from the high quality firm. These guys buy from, this would be I lower bar, from the low quality firm. Okay, that's exactly what we derived up there. Same things, nothing new. That's why I can move on quickly again, and this is related to our above example, what we already had in a monopoly case. The demand for the low quality product is only positive if its quality adjusted price is lower than that of the high quality product. Okay, and that means this is a quality adjusted price divided by quality level, and the low quality must have a lower price. That's same as the battery with the battery life of 1 year must have a lower quality adjusted price than a battery with a battery life of 2 years. Okay, that's exactly the same. And then the demand for low quality is just here, this I minus I lower bar, exactly what I showed you. And what we have here, we have demand functions. Once we have demand functions, we set up the price, we take the first derivatives and derive the equilibrium for given qualities. Standard procedure, solving for the first order conditions. So here is a profit, here again, profit per unit, and here demand. Okay, same for firm 2. Take here the derivative from profit 1 with respect to P1, and for profit 2 with respect to P2, and two equations in two unknowns, solve for P1 and P2, get prices. So here are our prices, our equilibrium prices. What we see here in terms of do they make sense? First of all, what is very interesting, of course, if both firms offer the same quality, if Z1 is equal to Z2, this guy here is 0. This is actually then 3Z1. Okay, the Z1 would cancel out here, and we are left with 3C over 3, which would be C. So if both firms choose the same quality, price is equal marginal cost, and therefore profit is 0. Okay, so no one or firms will always try to differentiate their qualities if they don't have any opportunity for, say, horizontal product differentiation. We will then see what is called vertical product differentiation. Okay, that's an important first result. And what you could always see is, of course, the price of the high quality product is higher than that of the low quality product. And yeah, that's what we typically much see. I think, I don't know, where I have a nice example in my notes. I have an example for say, offerings of broadband internet access with different qualities. You can look up this example and get some intuition about how that works in this example. Perhaps in order to get an easier, I don't know, I cannot copy that, but you can check it. I think you have it anyway, this example in your notes. I don't, perhaps we will have a similar problem in the assignment. Okay, so the point is the price of the high quality will be higher than that of the low quality, and the profit of the firms increases as their products are more differentiated. Okay, that's what we see in more detail here. If we substitute here the equilibrium prices, you see again, if qualities are identical, profits are 0. You also can see if you take a derivative or the derivative with respect to Z1, I think that's what's written here. I should move on like what we have here. So what is clear, the high quality firms earns a higher profit. You just compare this 2 theta Z1 minus C is larger than this theta times Z2 minus 2C, what is obvious. And profit of both firms increase if consumer heterogeneity increases, holding the number of consumers constant. So if you increase theta, that's a good thing, because first of all, the willingness to pay for quality increases, and at the same time, you get more space for, in a sense, vertical product differentiation. And what is really interesting is that the low quality firm is only viable if consumer preferences are what is called sufficiently heterogeneous with respect to quality. So only if theta is greater than 2C over Z2. That's exactly, only then this part is positive. Okay, and actually makes sense, because only then, of course, it's always positive because you have a square here, but otherwise the demand would not be positive. And this tells you, and that's a very important insight by the papers in the 80s, I think it was, by Schacket and Sutton, John Sutton and Avner Schacket. They showed that the so-called natural monopoly or oligopoly exists, and this is a lower bound to concentration if consumers are not sufficiently heterogeneous. I think I told you that with the example with the income distribution in Denmark compared to the income distribution in Russia. If you have like a more narrow income distribution, you will see much less product differentiation, and it might be that, or vertical product differentiation, it might be that the low quality cannot even survive there. You will only have the high quality be offered in that market. Okay? Now, how much product quality or product differentiation or quality differentiation, that's what you have here with the same reduced profit functions. What you can see is, and that's what I already started to explain above, the profits of both firms increase if the level of high quality increases. Okay, the profits of both firms increase if the level of the high quality increases. So just differentiate with respect to Z1. So also the low quality gains from a higher quality of the high quality because products are more differentiated. Firm 2 would choose a quality level which is strictly positive but smaller than Z1. Of course, you cannot choose a quality level for which there is no willingness to pay, but you want to differentiate. So products are differentiated, of course, but not arbitrarily a low quality. If markets are covered, we get maximum product differentiation. What is a covered market? I just get back to the slide we have here. Market covered means that our consumers are only here. So up there I gave you the example that you have consumers. This is something like income, and you have income up to here, but assume that the minimum income is this here. In this case, everyone would buy. So you don't have anyone who does not buy, because even this guy buys. And if given the minimum quality, given at this minimum quality, the price equilibrium is such that this guy also buys, that everyone buys, you get what is called maximum product differentiation. This is nicely explained in Short-Hero's textbook on page 296. I think that's what I wanted to show you here. That's what you get. In this case, even the one with the lowest willingness to pay gets a small surplus of positive utility. Yeah, this is really the last slide here, and actually it just makes a little bit of advertisement and actually therefore fits very well to the next topic we will discuss next week, because it advertises a paper I wrote together with Stefan Müller from University of Göttingen, which is exactly dealing with this kind of quality differentiation. Here we address the question: suppose you have an incumbent who produces a variety and who wants to deter entry. How does this incumbent deter entry? Suppose it cannot deter entry by choosing arbitrarily small quality, because otherwise the entrant will enter here with a high quality. So what we had in mind was, for instance, Lufthansa. How should Lufthansa deal with the entry of the Ryanair and all these no frills, these low-cost airlines? The point is, what this model here shows is that it's a good idea to also produce or introduce an extra brand, a medium quality brand. Okay, so in a sense, it's slightly opposite from what we just saw in the Gammawatt and Etsy case study on Boeing and Airbus. Here it shows you what do you get in terms of profit if you have only, and if you have to accommodate entry, that is to say. If you have only a single brand, this is exactly what your revenue will be, okay? And this is what your rivals' revenue will be. However, if you introduce, in this case, where you know this guy enters here anyway, and we have a third alternative here as well, if you, and I think I should use a different color here, if you introduce a further variety, what happens? So here you introduce your own Germanwings no frills brand, which is not so no frills like as Ryanair, not so low quality, but a little bit higher quality. If you introduce that, you get more competitive situation between the entrant and your brand, so that the price will actually go down, and therefore the revenue from this guy here will be only this. The revenue of the entrant will also be lower. And however, what this allows you, it allows you to increase the price of your premium product. And what you see is that if you see entry accommodation, it's always a good thing to introduce an additional brand, such a medium quality brand, in order to safeguard your premium brand. And the second brand is not here in order to gain market share, but to protect the premium segment from price competition. If you want to know more about that, I'm happy if you download this paper and read it, okay? I think it's a nice paper, and hopefully it gave you some idea about this whole topic of vertical product differentiation. Again, you saw that we get a lot of differentiation. Firms have an incentive to offer differentiated products, and it might be even a little bit involved if you are an incumbent facing some entry, and you might use such a second brand in order to defend your premium brand. That's it for today. Next week, we will start discussing advertising strategies by companies. We will discuss, in a sense, whether we will have manipulative advertising or whether advertising is informative, but you will have to wait for that until next week. I thank you and I apologize again for taking more time, but we are missing one full 90-minute lecture because our semester is shorter. So thank you for being with me. Available for further discussion in WebEx, and see you next week. Bye.